Excited to have with us today Dr. Randy Glickman, who's going to talk about some exciting research that he's done on ocular injury in rats, and let him explain who he is and what he's done and what he's tried to do, and he has some exciting results to share with us today. So, Dr. Glickman, thank you very much for joining us, and we look forward to hearing what you have to say.
Well, thank you, Jim. Thank you for inviting me to do this interview. It's quite interesting. So I'll be talking about the presentation we made at ARVO. We had a poster here yesterday with two posters, actually. I acknowledge my co-worker, Dr. David Rios, who worked on this project. And we're looking at coming up with better treatments for ocular blast trauma. This is a big issue in military medicine. What with the proliferation of explosive weapons and improvised explosive devices, ocular injuries now account for about 13% of casualties in recent combat
That's amazing.
incidents. It's a big impact, and so there's a lot of interest in developing better treatments for these kinds of injuries.
Okay.
So we decided to address one aspect of the treatment that's basically has no treatment options today, and that is blast injuries can produce a number of damage to the eye, physical damage, perforations, lacerations, penetrations, and that can be more or less repaired by surgery, but very often there's follow-on inflammation that causes ultimate loss of visual function. So there's really no good treatment for those conditions right now, but we decided to look at these class of compounds called specialized pro-resolving mediators as a potential treatment.
All right, thank you. And what can you tell us about your use of these new therapeutics in your study?
Absolutely. So first of all, what are specialized pro-resolving mediators? I imagine a lot of people aren't familiar with these class of compounds. These are actually metabolites of polyunsaturated fatty acids. And we looked at two members of this class of compounds, myrosin here on the left, and neuroprotectin D1, which is also known as protectin. And these are both produced endogenously. Myrosin is produced by macrophages, and neuroprotectin is produced by peripheral mononuclear blood cells. And it's also found in the eye. It's found in RPE cells, retinal pigment epithelial cells.
Sure.
So that's a clue that it may have important roles in the eye.
And I noticed in your experimental setup that you used the LKC UofT system with the BigShot Ganzfeld and not the Retinal device. What can you tell me about your decision on which technology to use in this study?
So I'll show you a little bit of our setup to lay the groundwork for that question. So we induced the ocular injury in the animals, these were rats, using this rather impressive instrument here, which is located at the U.S. Army Institute of Surgical Research, located at Fort Sam in San Antonio. And it simulates a blast effect. It produces a high velocity pressure wave of air that travels down the tube, and it produces a transient shown here with a couple of milliseconds for the positive overpressure. That's followed by a negative component, which produces a push-pull kind of stress on the tissue, and we think that's an important part of the injury. The animal sits in the tube here, and the blast wave will impact the eye in a lateral way. Now, my role in this project was to assess visual function in the animals. And we decided to use ERG and visually evoked potential to do that. And we were very fortunate to be able to find a whole LKC system that we could use at the ISR. And here's a picture of our setup. So we used the BigShot stimulator, and the animals will be situated on this holder here. We used the rodent contact electrodes that you offer, and we found this to be very effective for recording these potentials. And then we found an older setup for the software for the UTAS, but it all worked fine. And we found having the animal fixed in position with the Ganzfeld stimulator gave us more consistent recordings than, say, a handheld tester for this particular application.
Right. And you used the Naka-Rushton equation to analyze the ERG data. What can you share about that?
So when I was a young graduate student, this was a hot topic. It had been originally proposed by the famous researchers, Drs. Naka and Dr. Rushton. They proposed using a Michaelis-Menten type of equation to model the response of cone photoreceptors. This was recording from the carp retina. And it quickly became apparent this could be applied maybe more effectively to the sclerotopic ERG. And so it became a rather standard means of analyzing the response of the rods. I think in more recent years, it's not used as much, particularly in the clinical setting. I haven't seen much, but I thought it would be very ideal for this study because it would give us an objective way to measure the amplitude rather than just picking an arbitrary amplitude and say, okay, this is minus 30 dB, gives us so many microvolts. This would be a mathematical way to come up with a parameter to reflect that. So on the left side of this figure, you can see a typical intensity response series recorded from a rat. So with very dim stimuli, we have a small response, and as we increase the stimulus, we get higher amplitude responses. So we can plot these data out on a V log I curve and fit this particular equation. This is the form of the Knocker-Rushton equation to that curve. And the three fitting parameters we get would be the Vmax, the K, and the N. Vmax would represent the asymptotic amplitude as your curve rises with higher intensity stimuli. So that would be the Vmax value here. And you'll notice this excludes the rising limb of the ERG curve as you get to very intense stimuli. That reflects other than rod inputs. And then the K value would be the intensity of the stimulus that elicits a half maximal amplitude. And the N value is controls the slope. But I thought that the Vmax and the K would be really useful for this study because it would give us a measure of total retinal sensitivity, the Vmax, and then K could be a surrogate for retinal sensitivity. And then we could see how the blast affected that and how our specialized proresolving mediators might help to mitigate the loss due to injury.
And how long after the blast did you test the animal initially?
So in terms of the treatments, the animal got their first treatment the day of the blast, within an hour, and then daily injections, and this was injected into the IV system, intravenous system, every day for a week. And then we would do our first ERG measurement at 1 week post-blast. Okay. Now we also did a pre-blast control measurement, of course, so we had a baseline to measure. And then we measured again at 22 days and then 36 days.
And what were the results? What did you find?
So numerical results are right here. These data shown on the bottom of the screen represent two different rats. This was a rat that was exposed to blast but treated with the vehicle that we used to deliver the compounds. And so here's the Vmax value, is 523 pre-blast, and then post-blast, this was I think at 22 days, was 289, so pretty significant loss there. K value was a little bit higher, suggesting some loss of sensitivity, but overall in the project, I didn't see a significant change in K, but Vmax we did see.
Okay.
So with the treated animal, this animal received neuroprotectin, and so the pre-blast Vmax was over 600, and post-blast at 36 days was some loss, but still fairly well preserved, and K also showed good preservation.
So indicative of preservation over time of
exactly.
visual function.
In fact, we saw significant protective effects occur at about 2 weeks post-blast. We don't have a good explanation for why there was that delay, but perhaps it has something to do with the signal transductions that are motivated by these compounds. So this is the overall results of our project. We see, I don't know, hopefully the color comes up well in the image, but these purple bars here, this is the neuroprotectin. The orange bar is the animals treated with the maricin, and you can see that compared to the pre-blast level, these values were maintained. The Vmax was maintained, whereas the animals that were sham treated, these bright purple or reddish bars, you see they drop with time, and they become significantly depressed by the end of the study.
Now you mentioned that this was a proof of concept kind of a study.
That's
so
right.
Where does this study go from here? What do you hope
to
achieve?
Assuming that the rest of our animals show the same promising results that this first group did, we will look for further funding to look at different ways of delivering the drug. Just for ease, we use IV injections to the tail vein of the animal. But for practical application, I think other methods of administration might be better. Also, we'd like to have a better handle on the actual penetration of the drug in the eye. I mean, it seems that the drug is these compounds are getting into the eye because we're seeing that effect, but that would have to be determined in a more proper pharmacokinetic study.
So it sounds like if this plays out in the animal models and then can translate into the human models, this could be a game changer for those 13% of people who have traumatic events in people.
Ocular trauma is a common event in the civilian clinic, maybe not from blast weapons, but from accidents and from industrial accidents. So having a treatment to back up your surgical intervention would be important.
So this is some very exciting research, and I congratulate you on all you've done, and really look forward to seeing this translate to human model for all those who are viewing this video. Thank you very much, and thank you to your collaborator as well.
Yes. Thanks for having us here, and we enjoyed presenting our work.
Very good. Thank you.